Welcome to 9.3 equations. Remember to pause the video often, do the problems along with me, and complete the U-tries pausing before you check your work. These are the topics, the objectives, the standards, vocabulary, and concepts. So equations are a huge idea in mathematics. We use them when we have two different ways to express the same amount. So first in this section, we're going to summarize the different ways we use equations, and then we're going to actually solve equations. So let's talk about equations. It's a statement that an expression or number is equal to another expression or number. For example, we've got all different kinds of equations. So we just spent a lot of time in expressions. So this is an expression of 3.2 and it equals a number. This is an expression and this is an expression and they equal each other. So again, equations have an equal sign. And so it's always equal to or equals, etc. So here are different ways that we actually use equations to show calculations, like evaluating expressions. We can use them for identities, which are true for all values of a variable. We can use equations to relate quantities, like an area and different formulas, or they are to solve a problem. So for showing calculations, what we would do is we would say, okay, 5 plus 7 equals. However, so we would have kind of these two things. We would say, okay, this expression, 2 plus 3 times 4, we would use gems, right? And we would say 3 plus 4. So then it equals this and it equals that. So we take an expression, we use an equal sign. It's important though that when we use those equal signs as calculating the answer, we're understanding that it's not an equation so much as evaluating the expression. We can also use it as an identity. So things that are true always. So if we look at A times B plus C, this is a property here. When we distribute using the distributive property, we see that it's the same as AB plus AC. And that will always be true no matter what you plug in for A, B, and C. So we can continue with identities with numbers. They don't always have to just be letters or variables. So we can say, all right, this expression is equivalent to this because I can distribute my 23 to each of these terms. We can use equations to relate quantities together. So later in the chapter, we'll be looking at proportionality and y equals mx plus b. And so we can use equations to relate these relationships. And another one is area equals length times width, right? That is a formula for the area of a rectangle. We can also use equations to solve problems. A common way would be this word problem here. Tanya had some money after she spent $5. So first, remember grouping symbols first. So she spent the $5 first. She gave half of the remaining money to her mother. So far we've been doing this in previous sections 1/2 times, but then she had $18 left. And that is where we equal to 18. How much money did she first have? And so we could solve this equation after we model it, and then we can figure out what would make it true. So first, let's translate these sentences into equations using the variables that are indicated. So Malik's dog weighs 27 more pounds than their cat. Use D to represent the weight of Malik's dog and C to represent the weight of Malik's cat. So we know that the dog weighs 27 more pounds than the cat. So the dog equals 27 more plus the cat, and that would be an equation. The width of a rectangle is 2 inches longer than twice the length. Use L for the length and W for the width. So the width is, or the width equals, or the dog weighs, the dog is, right? The width is 2 inches longer than twice the length, 2 times. I'm just going to say 2 times the length. So the width is 2 longer than 2 plus 2 times L, 2L. During a softball game, the Hawks scored 5 points less than 3 times the number of points scored by the Eagles. Use H to represent the number of points the Hawks scored and E to represent the number of points the Eagles scored. So the Hawks scored 5 less than 3 times the Eagles. So we're talking about the Hawks scored 5 less than 3 times. So the less than is a little bit confusing because less than comes after. We need to know what happened first to take less. So we would do 3 times the Eagles less than 5. Less than can always be a tricky one. Subtraction can be a little tricky. And that should be a lowercase e. We should just match the capital symbols. All right, give these 3 a try and press play when you're ready to see the solution. And there we go. So now we're going to translate each sentence into equations. When appropriate, we're going to use the variable x to represent any unknown quantity, and we're not going to solve them. So here we're talking about the sum of 10. So we're talking about sum, that's plus, of 10 and. So when they talk about and here, that's the sum. The sum of 10 and the product of a number and 7 is 25. Oop, there we go. Okay. So product of and then sum of 10 and. So let's make sense of this here. So the sum of 10 and, so 10 and, the product of, so now we've got a multiplication, a number, we don't know, times 7 product is 25. Well, let's just reorder that. 7x plus 10 equals 25. We'll talk about standard form later, but we want to have our higher degrees in order from left to right and our constant terms last. So there we go. Is equal. In 15 years, a child's age will be 5 less than double their current age. Okay. In 15 years, so we're talking about in 15 years, the child's age, we don't know the child's age, will be 5 less than their current age. So actually, let's make their current age x. So in 15 years, so 15 from now, so they're this year's old now, and then in 15 more years, it will be 5 less than, remember less than is a little bit funny, double their current age. So double their current age, but 5 less than that. The area of a rectangle with a width of 2x and a length of x minus 3 is 100 square inches. So we have to remember that area is equal to length times width. So we do not know, let's see here, the area is 100 square inches. So we know that the area is 100. And it has a length of x minus 3 times a width of 2x. And we would just reorganize that. We would say like 2x, x minus 3. We wouldn't need the dot is equal to 100. So go ahead and give these 3 a try. Press play when you're ready to see the solution. And there we go. So now let's talk about solutions of equations. What does it mean to solve an equation, and what are the solutions? And some equations are true. For example, 3 plus 2 equals 5 always, and 10 equals 10 times 5 always. But some equations are false. 1 does not equal 0, 3 plus 2 does not equal 6. So, but most equations with variables are true for some values of the variable and false for others. So 3 plus x equals 5 is true only when x is 2 and no other value of x. So when we solve an equation, it means we're determining the values of the variable that would make the equation true, and we call those solutions. So when we look at 3x equals 12, what this means is what are the values of x that when I multiply it by 3, I would get 12? Well, 3 times 4 equals 12, and that's it. 3 times any other number does not equal 12, so the solution must be 4. So in elementary school, we solve these simple equations by maybe filling in the box, reasoning about these. So one source of difficulty is that the equal sign again here does not mean calculate the answer. What we're basically asking is what makes it true. So many will fill in the number 8 because 5 plus 3 equals 8. But again, to understand equations, we're saying when does this whole side equal this whole side? And so one really good way to help students make sense of that is to use a pan balance or a hanger diagram to show that these things need to be balanced. The equal sign is balancing the two sides. So viewing 5 plus 3, we've got 1, 2, 3, 4, 5, and 1, 2, 3, and then we don't know what needs to go there, but plus 2. And so if they were to put 8 on this balance, you would see that you have too many on this side here, and therefore that does not equal it. And we're going to pause here and come back in our next part.